And also, all class, in-class and online class are recorded and uploaded to our cloud server, Google Drive. So if anytime you have some questions, and then you can refer to a video recording. Okay. This will be okay. 예, 어저께 이거 안 했지? Well, I will just briefly go through this slide to emphasize one more time what is the strength of material, what is the materials, mechanics of materials. That's the subject we are covering this semester. So we need to clarify the concept of the strength of material. There are two keywords. One is the mechanics and the other one is the materials. Mechanics, as I mentioned yesterday, is the subject or subject about the force. Okay, force. Well, I'm not sure if you understand the Chinese. This is a Chinese to represent force. Okay, force applied to solid can be applied to solid. Solid means a material which can deform. Okay, it's solid, but it's not a rigid body. It is a body of a deformable body. Deformable body means how much deform? Well, it depends on the material and depends on the force. But in most cases, in engineering materials or engineering structures, deformation is very slight, very small. For example, this considered as a beam. If I apply the force, you can see the deformation. Well, this is a huge deformation actually. But imagine the airplane wing, it supports all the weight and all aerodynamic force, but the deflection is not that much big compared to wing thickness. But such a small deformation can cause a huge strain and stress. Okay, strain and stress. In terms of a strain, say we applied a certain force in this direction. Strain is that some order of 1% or 2%. So sometimes you cannot even see that. Sometimes you can, but in most cases you cannot see the strain. Anyhow, that is a deformable body. So this is a certainly deformable body, solid and deformable body, and all automotive is a deformable body, solid deformable body, and airplane and bike, all the bridges, all the buildings, almost every solid will deform under force. Okay, so the mechanics of materials or strength of material is the subject about materials deformation under force. Why so important? Well, when we design an airplane or automotive, every single part, even wing or stringer or ribs or skins, they have all their own roles. Role means that each part have to support certain amount of a force, and to support in supporting force, they have to deform because of the, as I said, stiffness and stress and strain. So again, strength of material is all about materials, mechanics, forces. Mechanics is all about the forces, okay? Forces applied to deform body. Now, for example, one very typical case is this spring. Take a look at this spring, and we apply a certain force on the right-hand side, okay? I'm pretty sure you know, you have seen the spring many times, but let's take a look at again. Here is the spring, and left-hand side and right-hand side, where there's a little bit different conditions. On the left-hand side, we kind of fixed. We have a fix, right? We have fixed, and this is the spring, and we apply the force, okay? Force. So spring, as you know, is well characterized or described by F equal Kx. Right? F equal Kx. What is F and what is X? Well, this spring alone, when this spring is subject to certain force, there will be some deformation, X, depending on this spring constant, K. Okay? So this is the F equal Kx is the K is a stiffness, and force is applied. The force applied to a spring, and X is a deformation. Well, this is pretty much elementary stuff, but the reason I emphasize again is that the whole concept of mechanics of material can be found from these simple equations. So F is the external force, and X is the deformation you can observe from outside, and K is the material property, and there is a certain geometric constraint. You have to fix somewhere, and then you apply the force, right? And now internally, if we take a look at any part, small part, there will be a small part, there will be also internal force, meaning that in every section, there will be some internal force which are transmit in a spring. How much? Well, in this case, is simply same as a force F, but sometimes structures complicate. We have to solve them using equilibrium equations. And also, when it deforms, it has to have a certain geometric deformation condition. We have to fix it. We have to. So whatever we apply the band, we always have a geometric constraint. It's different from different condition, right? Even though the same forces, depending on the geometric condition, the deformation and stresses are different. So again, there are three concepts. What are they? Force, stiffness, and deformation. Please keep that in mind, okay? That is the condition you have to have it to solve any structures, any member of structures for design or automotive or any structures, okay? Three concepts. We have to make sure this information are clearly defined. Okay, let's back to this flow chart. I hope by now it looks clear to you. As I emphasize, what do we have here? We have a force, right? We have a force applied to a spring. Spring is a material, right? Material, and material will have a certain geometric constraint where sometimes where is a fixed. So we have a deformation condition. These three concepts are externally given. So you as a designer, you have to make sure these information are clearly defined. Okay? And now, what are these next steps? This 5 step is inside material. As I briefly explained in this internal, each spring part will have to have or meet certain condition. What is this? Are they? They are force equilibrium. Okay, force equilibrium, or this force, externally applied the force, have to meet certain equilibrium condition, force equilibrium. If somehow force equilibrium does not satisfied, then the structure will have some acceleration movements. In other words, we have a fixed, we have a spring, we have a force, right? Now, let's take a look at this spring. And again, there is a equilibrium condition. Well, equilibrium condition simply said, we can say a F equals 0. All the F equals 0, and sometimes a moment equals 0. All the summation of force and summation of force and moment have to meet this equilibrium condition. Now, if take a look at the only spring, okay, this is a force. And where we have a fixed point, we have a fixed point here. This is a deformation conditions. Deformation condition. 이게 쓰다가 가는 게 있죠. 이거 좀 한번 찾아봐봐. 이게 여기뿐만 아니라 자주 일어나더라고. 꼭 파워포인트에서 이제 쓰다가 보면 옆으로 한번 구글링 한번 찾아봐. 내가 자꾸 잊어버려. So here we fixed, but somehow there should be certain reaction force, right? There is a reaction force. How do we know there is a reaction force? Well, try to use your pencil and then apply force. In the left-hand side, you feel something, right? You feel something. If there is nothing applied, this will move, you know, F equal ma, and this will be a subject of dynamics, right? But now we are considering a deformable body, which means that all the forces applied to a body have to meet force equilibrium, and then what we are focusing is the deformation of this body. So when we apply fix and there, how much forces we have to hold it? That is the unknown force R. Unknown force R. 왜 안 보이냐? Unknown force R. So if Fx equals 0, then F minus R equals 0. So R simply has to be F, right? So this is the force equilibrium. So now you can see what is about this force equilibrium. And what is the stress? Well, if we have a sections, very small section, there will be a small section, there will be internal force. And the stress is not clearly defined in the spring, but imagine instead of this spring, imagine instead of this spring, we have a certain bar. and then we apply the force and we fix it. Exactly the same story goes to this bar. And this one, let's say we apply the force, but now instead of a spring K, we have, anybody remember will be delta? Delta is what in terms of F, in terms of L, in terms of Young's modulus, in terms of cross-section A. Does anybody know this formula? This is too low. Okay, so delta should be a function of what? Cross-section and length and force and Young's modulus. It is clear, right? So simply, oops. Okay, so delta, well, let's say we don't know, we forgot the formula. There should be some relation, but that's okay. 왜 이렇게 좀 안에서 안 보여? Delta is certainly proportional to F. Let's say you increase the force, it double, the deformation will increase double, right? So certainly delta is proportional to F. Now, how about the A, cross-section? If cross-section is larger, the delta will be smaller or larger? Smaller. Yes. And how about the length L? If length L is larger, then delta will be larger or smaller? Yes. So it's proportional to here. Now, there is a Young's modulus which represents the stiffness or resistance to a deformation. So if the resistance high, delta will decrease, right? So simply like that. That's it. That's the formula. And in other words, F over A, what is, man, what is F divided by A? Okay, this is a stress, right? F over A equal, what is the delta over L? Delta, we can divide by here, right? What is that? That is a strain, right? And then E goes to here, is like that. So this equation can be written here. Oh, what is this? E and epsilon. So simply stress equal E epsilon, right? So concept of a spring can be equally applied to this solid body. Now in strength of material or mechanics of material, we will deal with a certain volume with the Young's modulus and dimensions and forces. So anyhow, this is all about the stress and about the strain and about the stiffness. Now strain and deformation condition, well, the relation is can be a little bit complicated, but here you can easily visualize the epsilon equal L over delta. Okay, and here delta equal or U equal 0 at x equals 0, which means here, okay, x equals 0. So anyhow, you can see overall relations, and again, let's divide two parts. This is the externally given condition, and this is the internal condition and internal concept. Say stress. See, this one is the stress and strain. This is a stiffness relation. And equilibrium, by the way, not only apply to this force, but also apply to internal stress. What does it mean? Well, if we cut this part, there will be a certain small part, right? Small part, there will be a certain force here, and this force F, this force F. And on the right-hand side, there will be a body like that. This is the F and this is F. So as you can see here, external force applied to internal, and internal will have all the F. F, 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 F. So this equilibrium condition is not only applied to external force, which help us to solve reaction force, right? But also this equilibrium equation will determine how internal stresses distribute inside the body. Okay? So equilibrium and stress. So equilibrium equation applied to this stress, and stress strain is the stiffness, and strain and deformation is the relation. So you can see that the three major concepts: equilibrium, material property or stiffness, and strain and deformation. Those three concepts are quite overlapped or linked by this concept. But anyhow, this is a concept flow, and this is externally applied or connected. And by the way, once you get the stresses and material property, in this case, how many material property do we have? Material property. In this bar, we have a Young's modulus is a material property, right? Young's modulus. What is the Young's modulus? This one, right? This is a material property. What else? And here, material property is the strength. Strength means that if you have a stress-strain relations, and I explained yesterday, right? And so certainly, if this stress reach certain level of strength or yield strength, what will happen? Material will yield. What does it mean, yield? Give up, and plastic deformation, no longer elastic. I give up, no longer elastic. So again, this is the elastic zone, but plastic zone, there will be a loading curve and unloading curve will be different. So in design-wise, at the airplane, one-time flight, and there is a certain deformation, which is not right, which is not desirable, right? So always a stress has to less than strength. So as you can see here, we have three material property. One is the stiffness, the other one is the strength. These are material property. You have to have them. So these materials, as you can see here, E and stiffness and strength. These are material property. Well, this one is, I only says Young's modulus, but there could be a Poisson's ratio. What is a Poisson's ratio? When you apply the load, this cross-section will shrink, contract, right? That is the Poisson's ratio. And Poisson's ratio, in most cases, how much? 30% on whenever you apply the load, there is a 30% will shrink every direction. So if you apply the force here, well, 30% shrink and shrink. If you apply the load, well, 30%, 30%. So there is the relation, but anyhow, these are stiffness property and strength property. Strength, there's a many different material behavior, such as plasticity theory, viscoelastic or viscoplastic, many different nonlinear behavior which is described after this yielding. Okay, see here and there, and very complicated behavior which is controlled by strength behavior. Those material property have to be given. Anyhow, if you use the steel or aluminum, you have to have a Young's modulus 200 gigapascal, 0.3 Poisson's ratio, and strength. Okay, so I'm not. This is not a new subject, of course. I'm sure you already know that, but I just rearrange the concept so that all the behavior inside the material and all the condition you have to look for as a designer to solve the problem. And I hope this is very clear. Again, this is not just for the spring, not for the only bar. It can be a beam, airplane, and all parts. As long as each part subject to some forces, and that part will deform. Any question on this subject? 핸드폰 다 집어넣어요? Okay, 핸드폰 수업 시간에 don't ever even try to touch your cellular phone. Okay, please. Okay, I hope that I emphasized enough. And now, in strength of material, in this subject and this course, well, yesterday we know that some students already taken the course, strength of material course 1, and some didn't. Well, some taken my course, some didn't. But it's okay. Okay, as I said yesterday, I will briefly go through all the core parts, core concept, which you have to know, okay, to move toward this strength of material too. But please, this is very important review, okay? So any subject is looks new to you, you have to go through yourself, or you have to ask me. In strength of material, we have a very important structures, 3 structures. What are they? They are first bar and shaft and beam. Okay, bar and shaft and beam. Well, what is a bar? What is a shaft? What is a beam? Again, let's take a look at these structures. This is not like shape like that. This shape has a certain character, which is the length. Length is much longer than these cross sections. Say H, H and B, and cross section A is a B times H in this case. And now, when we apply force which is in direction of this length, well, we already noticed there should be the same force from the deformation condition. In this case, let's call F, and this structure is called bar. So in the bar, structure support load in the same direction of the structures, okay? How about the shaft? Well, in the shaft, not because different material, not because of different dimensions, but only difference is the way it supports load. In other words, same structure designed to support certain load, torque. Then this structure is called shaft. And now, what is a beam? Well, beam is a structure, same material, same geometry, but only the difference is the loading directions. And this bending or that bending, you know what I'm saying? When I say double arrow, it is a moment. Is anybody doesn't understand what I'm saying? Moment? You are very quiet. But you have to understand the difference between this just one arrow and double arrow. And this is a force and this is a moment. Moment is a rotational force in this direction. So this is the rotational. So this one, say this one, we twist, okay, twist. Oops, something is broken. See, this is the mechanics. When I apply certain too much load, it deforms and it fails. I cannot fix it. You fix it. So, okay, it still works. So when I apply this way, so this one will rotate this way, right? See, this way. So this rotation, and I using these 4 fingers is like that. So this is a rotational motion, and this thumb is the arrow which represent these rotations. Okay, so this one. And now if we say this way, this will rotate this way, right? Bending, and this bending is represented by this thumb. So always a plane is the rotations and has always one a unique arrow which is the perpendicular. So it's very convenient to represent a certain motion. It's always the angle, I mean the perpendicular arrow which is perpendicular to this plane. Okay, this is the moment. Is it clear? And force is a moment. The force is pretty much clear, but sometimes you are confused with a moment. But all you need to know is this one. So anyhow, this one is the moment and bending moment, and this one is a bending moment. Bending moment means that this body will have a deform, or is this deform, right? So two direction deform. And this one we call moment. And another one force which will cause the bending is what? This is the moment, but another force which will bend will be this force, right? This one and that one. Oh, looks the same. No, they are not. This is a moment and this is a force. So when you apply force, this is all the forces and moments different from just concentration. So anyhow, you can have this force and that force. So let's call this a V. Let's make a coordinate system, X and Y and Z. So I just use a V. This is a V, but just for the purpose of clarity, I will add this sub-index Y, and this is a Z, and this F. F is a X. Okay, Fx. And this is a moment what? Y, and moment what? Huh? Z, and this is a torsion what? X, right? So this is the F, X, and this is the torsion X. This is beam. Beam is what? Beam V, Y, V, Z, moment. Moment Y and moment Z. So how many forces, how many moments? We have a three force, and three moment. Actually, you know, the twisting and bending is all same moment. Only difference is this way or that way. So they are moment and these are forces. So we have three forces, three moments which are applied to this long slender body. So depending on the loading direction, sometimes called bar, sometimes called shaft, and sometimes called beam. Now, as in the previous slide, we went through equilibrium and stress and this and that, and now this is the exactly same equilibrium, stress, strain, and stiffness, and so on. And in this course, I mean the strength of material 1, equilibrium condition is that we applied a certain force. Sorry, this is the F, and F, and which caused all the stress. For example, like this, and we apply, and inside all these stresses, all the stresses here, and summation of a sigma x over the A is the F. Okay, this is the equilibrium internally, and this one we pretty much the same. And when we have this, we have a torque, and we have all the shear stress distribution, and that is the equilibrium. So equilibrium and material stress strain relations, and shaft is we need a different material property, which is a shear stress, and stiffness is a tension or shear. So torsion is always a shear, and bar and beam is always a tension stiffness. And strain is related here. Well, this is just a summary, so I will just skip the detail. But this deformation is a function of x, means that, for example, when we apply the load and deform, here deformation is a 0, and proportional to x is increasing like that. So this is a strain. So this is each concept can be represented mathematically, but as you can see, all the same concept apply to each members. And each cross section, always in general, we can have a 3 force and 3 moments. And in this strength of material, the subject we cover is any kinds of a load and apply to a slender body, and then we explore how much stress and how much deformation. That was the subject we covered. Okay? Not much. Not much. Okay, so I hope this is clear. And let's have a 5-minute break. Okay, and then let's continue. Okay. So again, while I'm repeating basically same story, right? Same story, but the reason is simply help you to get used to this concept and flow chart. But without your effort, you know, you cannot reach that point. So you have to, you know, keep thinking, and also you have to pick a certain very simple example, and you try to go through all these examples. Okay, this is very critical part. So this week, and then as you can see, every chapters, I will show the chapters. Can you read this chapter name? Yes. So force equilibrium. Why? Well, as we can see here, the first concept is the force and force equilibrium, right? That's why the first chapter is all about the force equilibrium. Okay, that is the chapter 2, first chapter. And here we define the force and moment and all the equilibrium condition. Basically start with the general geometry and all kinds of load. And sometimes you have a reaction force, constraint. Sometimes you constraint, and this is applied the load. See, this is a material property. You apply the load with a certain geometry deformation condition, right? Always three: deformation condition and material properties and forces. Now, there will be a certain reaction force, and reaction force. How do we calculate the reaction force? Yes, force equilibrium. We need a reaction force to move next step. So for that purpose, we define the moment. We define went through all force and moment and 3 force equilibrium and 3 moment equilibrium. So this is a chapter about the force equilibrium. And sometimes, very important point is that how many equilibrium equation can we have? Only 3 force, 3 moment, right? These are force equals 0 and moment 0. Force is a vector and moment is also a vector. So always 6 equations. Now, if we have a reaction force, somehow we have a fix, and reaction forces, number of reaction forces are more than 6. Can you solve that reaction force? No, we cannot. So this problem is called statically indeterminate. What is a statically? Well, force-wise, force condition only we cannot solve. So statically indeterminate problem. But if the reaction force is somehow less than or equal to force equilibrium, then reaction force can be solved by only considering equilibrium equations. This is called statically or equilibrium-wise reactions can be determined. So statically determinate. So it's very important to distinguish whether this problem is statically indeterminate or statically determinate. Why this can be important? Well, the solving procedure can be very simplified. In this flow chart, this flow chart, let's say statically determinate. Determinate means that this is just force and reaction force all can be determined. And this problem all determined itself. Problem solved. All the reaction forces solved without considering the bottom condition. But statically indeterminate problem, this cannot be solved because these are coupled. So all the unknowns have to solve all together. I will go this case, not much time, but for example, but anyhow, this is a statically determinate and indeterminate, and this is the force equilibrium. What are the next chapters? Next chapters are about the deformation. You remember the bottom, deformation, strain, stiffness, stress, and equilibrium, right? So we touch the equilibrium, and at the bottom part, we considering deformations. And what is the deformations? I'm sorry. I will It's not right. Deformation is not bottom part, the whole parts. Okay, this is the all about this statically determinate and equilibrium and force equilibrium and so on. This is just a simple application to the concept applied to a simple case such as this. We have a two spring inside and outside, and apply external load W. Okay, this is the case. I need to assign you this week task for your group task. So please pay attention, and you have to work together. Okay. So this is the chapter about the chapter 3 is the apply. The considering analysis of deformation. In this chapter, we are considering overall 5 steps using simple cases. And chapter 4 is the uniaxial loading and deformation. This is the very simple definition of this, which I just mentioned. You know, the P over A is the stress, and delta over L is the strain, and Young's modulus. So this is the brief touch of this loading and unloading deformation. Now, here is the stress strain. And what is the stresses? Well, simply force divided by A. But in three-dimensional case, you would have a little more complicated condition. In 2D, you could have an arbitrary cross-section. And in 3D, you have a more generic cross-section. So now you have to consider generic cross-section and all the forces in this way, and that way in each cross-section. So this is the definition of a stresses. And there is a certain subject about the transformation, which is extremely important to understand the stress, which I will explain a little later. And chapter 6, stress. Now this is the chapter about the material property. Okay, stiffness. And next one is the strength. You know, the 5 plus 1. Strength and stiffness, strength, you compare and then we apply this concept to a shaft and bending, and that's the end of the whole course. Okay. So don't feel that, oh, this subject is really big, while in fact it is not. It's simply A plus 1 flow chart. We consider a bar, and first we review each one, deformation and stress and strain and stiffness and equilibrium, and then whole concept applied to a bar and shaft and beam. Okay. That's the end of the course, which we covered. Okay, so as an exercise, as I mentioned, I will get back to this problem and what is this, and I will clarify the task you need to do together. Oh la la. Okay, first, I will explain what is this about. Now, calculation of a statically indeterminate problem. Well, indeterminate or determinate, okay. Some may understand, some may not. That's okay. Forget for a while. Now pay attention to the case of this. two springs are supporting one big load. Okay, two spring is a same axis, and small spring inside and bigger spring outside. And two spring, the lengths are same, and one load applied to a two spring together, and this is the case. Now, these are given, okay? Make sure you have force, materials, and deformation condition, okay? This is not to just solve the simple problem, but to make sure you follow 3, 5, 1 concept, okay? So even though it's pretty much simple, try to follow the steps. Now, what to find? What we try to find is how much it deformed, how much the load carried by each spring. Okay, let me repeat again. What we want to find is how much it deformed and how much load carried by each spring. 2시 15분까지? 15분인가 20분이에요? 네? 15분? Okay. 5분 남았네. So this, I will just briefly show you how to solve it. So first, what is the given? What to find? And F1, F2, and X1 and X2. Again, F1 is the force carried by the inside the spring, and F2 is the force carried by outside, and deformation is the for each spring. So this is the inner, and this is the outer spring. Okay. So these are a force and deformation we are trying to find. And what are the given? Well, given is the W. These are force. This is the force applied. And K1 and K2. What is the K1 and K2? Okay, stiffness. But try to visualize all the flow charts. Okay, not just focus on this, but try to visualize. So this is a spring, our stiffness, and what is the D here? We have fixed deformation condition, right? This is a deformation condition. So we have force, we have stiffness or material. So force, material, and the bottom has the deformation condition, right? So we got those three. And now inside means that each spring, what is the force carried by spring any point, and what is the deformation, so F1 and F2 and X1 and X2. That is the some values we try to find. Now, before we solve, make sure we have a number of unknown equal to number of equations. So as you can see that force equilibrium, now you see the force equilibrium, okay, force equilibrium. To do so, we need to draw this one, say W. So these are W, and there is the F1, and outside is F2, right? So force equilibrium wise, if this is X, we can say all the total force X equal, now you have to pay attention to a direction. This is a plus, but to do so, you have to make right coordinate. Always try to use coordinate system. Otherwise, you can make a mistake. So F1 plus F2, and this W is the minus or plus? Yes, minus, because we indicate in upwards. So minus W. So that's why we got this equation. Now we have how many equations? Only one equation from equilibrium. Why? Oh, you said three force and three moment equilibrium. We should have a 6 force equilibrium. Well, yes, for the three-dimensional body, but we have only one dimension, so we only have one equilibrium equation, right? But conceptually, this represent 6, 1 out of 6. And how about the deformation material property? You remember this equilibrium, and there is the stiffness relations of which represent the spring. And each spring, we said there's F and spring as X. So F and X and we have X1 and X2, right? Very simple, but this represent stiffness material properties. Now, the most important concept is the bottom part, deformation conditions. What is that? Deformation. You know, two springs, they have to deform together, right? X1 equal X2. Very simple. Imagine X1 is the larger or smaller. That cannot happen, right? That cannot happen. So in this case, in this problem, this deformation condition is the most critical one. Of course, this force and equilibrium material property is also important. So now let's count how many equations. 1, 2, 3, and 4. Right? How many unknown? 1, 2, 3, 4. Aha. Now we have a 4 equal 4. Then you can try to solve. I'm sure you don't have to. You got all F1, F2, and X1 and X2. So again, this is a typical case of a statically indeterminate. Why is called indeterminate? Because of force equilibrium equation, we have only one equations, and this F1 plus W, but this is a two unknown, right? Two unknown on one equation. We cannot solve it until you consider these conditions. If there's a spring, is only one spring, like that, you know, what's the reaction force? Well, F minus W, Fx equals 0. We don't have to go through, just simply F equal W, right? Very important. This one, oh, reaction force is solved by only equilibrium, which means that it doesn't matter the stiffness. Regardless of the stiffness of this spring, or as a force is the F, right? But in this case, it's a different. Why? This is all coupled. As you can see here, X deformation, the amount of deformation depends on not only this, but also all the material properties. And F1 is the K1, X1. As you can see that, it all depends on K1 plus, K2 plus, K. It depends on the K, which is different from here, right? Clear? Okay. So anyhow, I really hope this is clear. I mean, this has to be clear. Follow all the steps, okay? But now, here is your task. Okay. We have four springs, one top, and on top we have a W1 weight, and middle there's a W2, and at the bottom we have a 3 spring all aligned. Okay, and these are given, clearly given, right? All the spring and all the forces. And now to find is that say this is the X1 deformation and X2 and X3 and X4. And of course, how much force and how much force, and this is a force. Okay, you know what I mean, force and X, right? Of each spring. So this is the group test, and so due next Tuesday. Huh? Yes. So this is a fourth spring and third, second and third and fourth spring. Okay. It's a Tuesday. Yes, neglect spring weight as we did here. Okay. Pretty much the same as this. Any others? Right. Now, this is the problem. I'm sure this is a simple, yet clear to you. And now you need to work together as a group and put this into your PowerPoint and symbol. And using Excel, you enter equation, give us some number. Number means you specify your own numbers. You will get, for example, you will get equations like that. You can enter in the Excel, right? Excel, and with this input, and this will be output. Okay? So, of course, you have to drive symbolically and then enter the Excel. Again, I'm with you and watching. I'm not a watching dog, but I just want to be with you. Okay? Any further questions? Yes, in Excel, you enter the formula, but input value, you can specify any value you like to have. And then you can take that result in copy into a PowerPoint. Here are the symbolic solution, but this arbitrary number, we get this much numbers, right? You don't want to using calculator, but instead you use Excel, okay? So I will check your Excel myself as well. Any other questions? What do you mean? In the writing equations, it's up to you. You can have a word processing in the PowerPoint. You can handwritings and then copy and paste. It's up to you. As long as you show some collaboration. Any others? Just try to impress me. Okay? I'm ready to be impressed. Okay, thank you, and then see you tomorrow. Next week.